Welcome to a new video. In this video, we're going to learn about synthetic hydrographs. And if you remember from the previous video, when we saw for our unit hydrographs, we were given flow values, right, at every single time step. However, in our in storms, usually we don't have every single value for each single time step. That's information that is usually hard to get, so we need to work with synthetic hydrographs. When we have the values, we can just plot them and get nice plots of hydrographs. But since we don't have those values, we'll have to make some synthetic ones. They're gonna look like this, just a triangle. It's over exaggerated approximation of how our hydrograph will look like. So that's going to be the purpose of this video. Now, we have a lot to cover in this video. We have 4 problems. So let's get started. 6.1. For a 50-acre single-family residential area and a rainfall intensity of 3 inches per hour for 1 hour, develop a hydrograph using an assumed average runoff coefficient from table 6.5 and assume the rational triangular hydrograph shape. What is the peak discharge if a maximum runoff coefficient is assumed? Um, so we are going to use for this problem the rational formula or the rational method. Now, this method is actually widely used in my experience, and I'm a student, but so I'm done an internships, and one of my internships, I saw that developers would submit their stormwater reports, and they would use this method, the rational formula, or the rational method, also called, to develop what is going to be the peak flow. So this method, even though it's very simple, it's widely used profession in the professional field. Um, and this consists on something that we have already covered, Q equals CIA. And that's the main formula for the rational method. Now the book mentions KCIA, K prime, where K prime is just the the conversion factor to to go from inches per hour of the intensity times the acres. If we multiply these two values, it's going to be very, very similar to 1.008 cubic feet per second. And we have covered that in a previous video. So since it's very close to 1.008, we can just avoid it. And in this problem, it's asking us for the peak discharge, and it's giving us the type of area that we have. So in table 6.5 is where we can find our C values or runoff coefficients. Remember that QCIA only means is out of all the rain that is falling, how much water is going to run off, because not all of the water that rains actually is transforming to runoff. Some of it is lost due to evaporation or infiltration. Now, it's hard to know what that C value is going to be. Well, that's why we have this table here, table 6.5, that helps us get a runoff coefficient depending on our type of soil or a type of land that we're working with. In our case, we're using single family residential. So we're going to use, I believe, let me see, single family, yeah, it will be this one, single family, which goes from zero point 0.3 to 0.5. To develop our hydrograph, we want to use, and the book uses zero point 0.4. So we want to use that 0.4, the intensity is 3 inches and the area is 50 acres. So to get the Q, all we need to do is just multiply all these three values, right? Once we have found, determine what the right runoff coefficient is. And that gives us about 60, and this will be cubic feet per second. And remember, inches per hour times acres is pretty much about 1, so you'll get cubic feet per second. And this is the value of Q. Now, if you look at this hydrograph template here for the rational method, you'll notice that this template is used assuming that the time of concentration is going to be equal to the duration of the rainfall. If you guys remember, I think it was video 17. Let's see, maybe video 16 that we worked, yeah, that we worked with times of concentration using the Kirpage and RCS. And all the time of concentration is how long it will take for the drop of water. The farthest drop, not necessarily the farthest, what's the longest time that water of the rain is gonna take to exit. Hopefully you watched that video. So if you did, this will make a lot of sense. So that's what the time of concentration is. And it's like assuming the duration of the rainfall is exactly the same or very similar to the time of concentration. And that's why we use, here we are told that our storm is 1 hour. So we can assume if we make our own table, we can assume time and then we have the Q values. So at time 0, Q will be 0. And then we have that the intensity is 3 inches per hour and the duration of the storm was 1 hour. So the time steps are per hour. So by the first hour, we assume once the time of concentration equal the duration is equal 1 hour in our case. When 1 hour is over, we have reached our peak, which in our case we solve that is 60 cubic feet per second. And by this next hour, which is also time of concentration, which is equal to the duration, and our duration is 1. So by the next hour, we'll have 0. So all you need to do is plot these values. Let's see, chart, and you'll get something like this. And this will be a very rough approximation using the rational method of this storm with this intensity in an area of 50 acres. So this is, I would say, the solution for this first problem. Now remember these characteristics of the rational method, Q equals CIA. Because now in the next problem, we're gonna use a different method that is the SES method. And it's gonna look a little different, and I'm gonna try my best to explain why and how it works. Problem 6.4. Calculate the peak runoff from a residential area with similar watershed soil and surface characteristics. The area is 20 acres in size with 40% imperviousness. Use rainfall intensity of 3 inches per hour for 1 hour. So our storm is for 1 hour. Do the calculations by using the rational formula and the SES typical hydrograph procedure. Compare results and discuss assumptions. The pervious area does not contribute to runoff. So we have some information here, and we are given that the 40% is impervious, which in other words, it means it's talking about a runoff coefficient. So that will be 0.4. Our inches is 3 inches per hour, and our area given is 20 acres. And this is inches per hour. Let me move this here. This is inches per hour. So we need to use the rational formula or the rational method that we already know, and the SES typical hydrograph procedure. It's very simple. One is CIA, and the other one, the SES, is 0.75 CIA. So to find the peak flow, all you need to do is, as we did before, multiply C times I times A, and this is going to be CFS, cubic feet per second. Now, for the SES, it's going to be 75% of that, 0.75 times this value here. And yeah, you have found your peak flows of both for both cases. Now, if you want to plot them, we have here, let me, before I plot them, it's gonna look like this. These are, like, I would say, the templates of each method. The rational method, we already are familiar with it. We just saw in the previous problem. The SES is a little different because the falling length of the hydrograph is a little longer and its peak is lower. So if you notice here, the rational method gives us 24 CFS and the SES gives us 18. So when we plot it here, we get 24 for the rational method and 18 for the SES. Now, the volumes of water, the rainfall was the same. The amount of water that fell on the ground and is running off for both cases is the same. Therefore, if the peak flow is lower, the falling limb needs to be longer. So the area under the red line and the area under the blue line are the same. So that's one of that's one of the assumptions that we make for these two plots. Now, how to determine how far out the falling limb is gonna get before it gets when it gets to zero is multiplying 1.67 times the time of concentration, which in our case, remember, is equal to the duration of the rainfall. And the rainfall is 1 hour, so all we need to do is we already have reached 1 hour, so we need to multiply 1.67 times our duration. In our case, is 1 hour, so it will be 1.67 hours farther out. So if you plot these values, this is for the flow of the rational method, 0 at hour 1 is 24, at hour 2 is 0. And this is for the flow of the SCS method. At hour 1 is 0, at hour 1 is 18 when it reaches its peak, and at hour 2.67 is 0. Now, how I found 7.22 at hour 2? All I did was finding it's pretty much like um, I would say linear regression, but it's not quite linear regression. It's easier or more accurate if you do you find the slope. If you find the slope of this line, you have the peak flow value and the time, and you have 0 and 2.67. So you can just find the slope, sorry, and then find what the value will be when x equals 2 right here, when x equals 2. And that would be 7.22. I already did it, so I don't have to do it here. I hope you can do that easily. And I think this is it for this problem. Do the calculations both for both methods. We did it. We found the peak flows, and then we compared the results and discuss assumptions. And we did already that. If you notice, the only difference so far in these two rational and SCS method is the falling limb. In the rational method, we consider the rising limb and the falling limb time the same, and they're the same as the duration. So it's gonna be, I would say, easier to find that. For the SCS though, since the NCS lowers the peak, it needs to expand the falling limb, and we do that by multiplying 1.67 times the time of concentration. Now, in the next problem, you are going to notice is it this problem? No, it's actually the next problem that you are gonna actually understand all these methods and how to know how far out the falling limb is gonna go. But before that, let's do 6.13. In 6.13, we have a county requires use of the 1 in 10 year storm frequency for the detention basin design. All it is like 10-year return period. Says use the IDF curve for Orange County. Then what duration, 1 or 6 hour, produces the largest detention basin? If the output hydrograph is 10 cubic feet per second, the watershed area is 50 acres, the rational coefficient is 0.8, the output hydrograph starts at 1 hour at a constant 10 cubic feet per second, excuse me, and the time of concentration is 1 hour. Only compare using average intensities and the rational formula. Now, this is the way the book formulates this problem, which to me is very confusing. But all it's saying is for the 10-year return period, compare the 1 hour or 6 hour intensity storm and see which one is going to require a bigger detention basin. Now it's not just like it's giving you we need to find the inflow volume of water into the detention basin, and it's giving us a outflow rate of 10 cubic feet per second of the retention basin. So while we are getting water, we're also the basin is also getting rid of it at a rate of 10 cubic feet per second. Considering that, we need to find which storm is worse, which storm requires more volume of water. And let's start by, let's assume we don't have these two values. We need to find the intensities with the IDF. And just a quick recap of how to do it. Using an IDF, you just go for the return period you are interested in. In our case, it's 10-year return period, and then you go for the hours, the time of the storm. In our case, we want to know for 1 hour and 6 hours. 1 hour is 60 minutes, so you go up to the 10-year return period, which will be around here, and I would say it's about 3.1, and that's our intensity in inches per hour. Same way we did with this 6 hour, and we get already is one about 0.83 inches per hour. So that's how you get these two values of intensity. Now, if the duration of the storm is 1 hour and our intensity is constant during that hour, we want to find the volume. We just multiply inches per hour times hour, and it's going to give us inches, the volume in inches. So in our case, it's going to be 3.1 times 1. It's going to be just 3.1. And same way with the duration of 6 hours. The volume is going to be our intensity times the 6 hours. So it's gonna be in inches, our volume in inches is gonna be 4.98. Now it's asking us kind of like two questions. We need to know the differences in volume. Uh, this is just the volume getting into the tension basin. We need to account for the outflow. However, since the outflow for both is going to be the same, 10 cubic feet per second, we already can see that the 6 hour duration is going to require more, more volume of the detention flow. So it's going to be bigger, right? Because the rate out of it is going to be the same. So we can already see the 6 hour storm is going to be worse. But besides that, we also need to find the Q peak for both. And we are given this, we need to use the rational method, CIA, and we are given that C equals 0.8. The intensity we found is intensity for each, and the A is equal to 50 acres. So to find the Q peak, the peak flow for each one of them, we're gonna do CIA. So it's gonna be C times I, the intensity, times A. And this is gonna be equals the same, C times our intensity times A. And we get 124 CFS, 32.2 CFS. So that's that part, finding out their peak values for each storm. And now let's these inches converted into cubic feet to know and consider. Once we get the volume in cubic feet, we can also get the output volume during that hour in cubic feet and then subtract them. And that's how we get how big the basin needs to be. Our inflow minus outflow is going to give us the volume. So let's say inflow. Let's actually do the 1 hour storm inflow, and then we have outflow, and then we need to do uh, the the tension basin volume, which is gonna be inflow minus outflow, and we're gonna do the same with the 2 hour. Let's copy and paste. Okay, good. So we have we have that. So inflow, that if you remember from our equation that the runoff is gonna be equals to C times P. This volume is, remember, the volume of water that we are getting on the precipitation. So we want to go know our inflow in the runoff. We need to multiply this 3.1 times 0.8, which is a runoff coefficient. So that's going to be inflow is going to be equals to 0.8 times our precipitation. And this is going to give us 2.48 in inches. If we multiply this let's say this is giving us the value in inches, parentheses, we multiply this by the area, which our area is 50. Now we need to convert those inches into feet and the acres into square feet, and we do that by to convert first into inches, we need to multiply by 1 over 12, and then to convert the acre into square feet, there are 43,560 square feet in 1 acre. So we get, yep, we get 450,120 cubic feet. That's our inflow in cubic feet. Um, and why am I doing all of this is because the book answer actually gives the answer in cubic feet. So if you just solve it by saying like, hey, this is bigger than this, so this will need more, um, probably you'll get points docked. So we need to convert all of it in cubic feet. Now the outflow is going to be, the duration of the storm is 1 hour. So we need to multiply 1 hour times the intensity of the outflow or the rate of the outflow, which is 10 cubic feet per second. Now we have hours and seconds, so we need to convert, get rid of the seconds and get rid of the hour, so we get only cubic feet. And to do that, to get rid of the hour, we need to multiply by 3600. There are 3600 seconds in 1 hour, and that's gonna give us 36,000 cubic feet. So to know the volume of the detention basin, we just need to subtract one from the other. This is from 45, we need to subtract the outflow, and we get that to a 1 hour storm, we need 414,120 cubic feet of volume for a detention basin. Now we do a very similar approach with our inflow for the, this is actually not 2 hours, this is 6 hours. We're comparing the 1 hour with the 6 hours. And as we did here, we are going to do the precipitation. The runoff equals runoff coefficient times the precipitation. So that's going to be equal to 0.8 times the precipitation. The volume that we're getting is 4.98. And then convert all of that into cubic feet by, well, we need to multiply by the area first to get it in volume, and then divide what we did, divided by 12, and let's multiply 43,560 divided by 12. It was the same. So we're gonna get this value. This is cubic feet, and now outflow is gonna be the same, but instead of 1, we're gonna do 6 times the 10 hours, uh not the 10 hours, the 10 cubic feet per second, multiplied by 3600, and I need to put an equal at the beginning, and we got 216,000 cubic feet. And all we need to do here is extract both of these, and we get, as we expected, that for a 6 hour storm we're going to need a bigger um, detention basin. But now we have the values in cubic feet and even including the outflow rate of each detention basin, and this should be your answer for this problem. Now let's move on to the last problem, and this one, um, hopefully with this problem you get to understand uh, the rational method, the SCS method, and how their falling lengths change depending on the type of method that you're using. And for that, we're gonna use table 6.6 to understand it better. Let's do 6.16. Let's read the problem. Imagine a 100-acre area before and after it is developed. Before it was natural land, and after it has houses and roads. We want to compare how water flows off this area during a big storm, both before and after development. Key information. The watershed size is 100 acres. The design storm, the biggest storm we are considering, is 5 inches of rain per hour. This is our intensity, inches, 5 inches per hour. Now, we're given runoff coefficients for before and after development. Which these are, as we know, these numbers tell us how much of the rain will become runoff, which is the water that flows away. Before the development, we have a 0.2, meaning 20% of the rain becomes runoff. And after the development, we have a 0.4, meaning 40% of the rain becomes runoff. We have seen that with development, we get more runoff, so this makes sense. Now, the hydrograph shape. This describes how the flow of water changes over time during a storm. Before the development, the shape is known with a peak attenuation of 0.31. This peak attenuation reduces the peak to be more realistic according to the area we're working with. And I'm going to explain that a little more so you understand conceptually what it does. And after the development, we'll assume the shape is similar to the standard SES peak attenuation shape. What we need to do, first, we need to estimate the peak discharge. Second, we need to draw hydrographs for before and after. And then third, calculate the storage volume. Now, peak attenuations, what is that? Let's look at table 6.6. We have, in table 6.6, we have general descriptions of different types of land, rational formula, urban, steep slopes, mixed urban, rural, with different types of rural. Now, if you remember, let me go back to, actually, I have the question here. We have been using peak flow equals CIA. Now, in this approach, we actually, instead of just being CIA, this formula has been peak flow equals K CIA. Why haven't we involved K before? Is because we've been using the rational formula where that K value, it's 1, and we've been using areas of acres. So that K value is 1, so you don't need, that's why we haven't been putting it in there. Now, if you remember when we did rational formula, we did 1, and then we did the SES method, we put 0.75 in front. Here is the reason. When we use typical SES or the SES method, we use 0.75 times CIA. K becomes 0.75. Now, that value is going to change to reduce the peak. You remember the rational formula gives us a pretty high peak? Where was it? Here. The rational formula gives us a higher peak, but the SES gave us a lower peak. So that peak is going to vary depending on the type of area or method that you are using. Like, let's say you want to use a rural slide slopes, which is actually what we're going to use in this problem. We're given that the peak attenuation is 0.31, which is right here, which belongs to rural slide slopes. So we would use 0.31 times CIA. So that's the peak attenuation, and that's what it means. Because the peak of the flow of the hydrograph is gonna lower or be higher depending on the type of area that we are working with. Now, that's the peak attenuation factor. Now, if you remember from problem 6.4, the fact that we changed the peak flow, it made us so the falling limb is longer, right? It takes longer to for the water to come out after it's reached its peak. And as we said before, this is so the volume, because the volume of water is the same, so we need to be consistent. Changing the peak would change the falling limb, which is we're gonna need a falling limb factor. And all we do is multiply the time that it gets us to get to the peak times each of these numbers. If you remember from the rational formula, the rising limb was a time, the time that it takes to rise to the peak was exactly the same as the time it got us to get it to the bottom, to 0. And it's because the K is 1 and the X, the falling limb factor, is also 1. For the SES method is 0.75 and the falling limb is 1.67. So we multiply 1.67 times the time it takes us to get to the peak. In our case here, we're gonna use 0.31 and we're gonna multiply whatever time it takes us to get to the peak times 5.5. Hopefully that makes sense conceptually what we're doing. Now let's move on to solve the problem. We are given the information that in the pre-development, we now know that is the rural slide slopes. K is 0.31. We are given a 0.2 of runoff coefficient. Our intensity is 5 inches per hour and our area is 100 acres. Now, because our K is 0.31, now we know that X, our falling factor, limb factor, is 5.5 here, 5.5. And now all we need to do to find the Q peak is multiply now K times C times I times A. So let's do that. Equals to K times C times, times I times A. And it gives us A, this is in CFS, 31 CFS. Now, I'm gonna explain how to. I've already done examples of how to use this X, but let's find the Q peak for the post development now. Before we do that, and that's gonna be exactly the same. Equals to K times C times I times A. And that's gonna be 150 CFS. Let me see if I'm getting this value. Yeah. Now, this is how you will approach this problem. However, the book doesn't mention this in this problem, and that's very tricky. But the solution of this problem actually let me have you to use a similar but also different formula, because this formula is only used as it is. This formula is only used when our duration of the storm, I have here, when our duration of the storm equals our time of concentration. That's when we use Q equals KCIA. But the solution of this problem is assuming that those two are not equal. It's assuming that the time of concentration is longer than the duration of the storm. In other words, it's like the storm started, the storm finished, and water, the water hasn't, the farthest drop of water hasn't reached the runoff, not the runoff, hasn't reached the gauge at the end of our watershed, which is actually very common. So you can use this formula only when the duration equals the time of concentration, which, according to the book, it happens only for storms that are about 20 minutes. So if the storm is higher than 20 minutes, um, you might want to use this other formula, which is the same, Q equals KCIA, but all of that divided by the duration of our storm over 2 plus 0.6 our time of concentration. So it's divided by all of this. So if we account for that, yeah, I think the book mentions cause lag time like this. Our lag time, what it's doing is Q equals KCIA divided by D over 2 plus L, which is the lag time. And lag time is 0.6 time of concentration. So we have solved actually for the numerator. Now let's solve uh, for the denominator, which will be, if we solve for the denominator, it will be duration over 2. The duration of our storm is 1, so it's going to be 1 over 2.5 plus the lag time, which is 0.6 time of concentration. And our time of concentration is 1. It's actually, what are we using? Yeah, 1. If you notice here, that doesn't make sense because our duration is 1, our time of concentration is 1, so they both should be, they're the same, so we should just be using this top equation. But, the book is sometimes messed up. And if you want to get it right, according to the book, you need to follow this. But now like if the duration and the time concentration are equal, you just use this equation. If they are not equal, you need to divide this by D over 2 plus L, which if we divide this 150 and divide it by what we got, the denominator here, we got 136. And that's what the book actually will give you as the answer. So far we have found the peak flow of the pre-development and the post-development, which is what we found here. Now we need to find the use the falling limb factor to find how far out the falling limb is gonna go. Let's make our time. This is Q with the rational method. This is Q with the SES method. And Q with the rational method, we got 0. We know the storm is gonna be, the peak is gonna be reached at 1, and then the falling limb is gonna go how long it took to get to the peak, which is 1 hour. times 5.5, which is our lean factor. Oh, so let's do 1 hour times, in our case, it's gonna end up being 5.5. So at time 0, we got 0 flow. 1, we got 31. And at 5.5, we got 0. And we do the same approach. Let's do the same with the post development using the SES. So we have 0, 1, and this is going to be how long it took us to get to the peak, which is 1, times 1.67. So this we got 0, at this we got our peak 136.4, and at 1.7 we got 0 again. Now, if you plot these two values, these two graphs together in the same plot, I've been having trouble to plot them together here. Uh, it's way easier for me to use Excel, but here with spreadsheets, I have a hard time. So I don't want to lose most of your time, so you can do this on your own. And if you plot this also as well, chart, you're gonna get something like this. Now, if you plot them both in the same plot, you're gonna get something. I wish I have an image to show you, but you're gonna get that the volume, like let's say this one reaches higher. One is way longer, you see. So this one here is gonna be plotted somewhere higher up here, very high, up to a 136, and then fall to 1.7, somewhere like here. So all you need to do to compare the volumes is subtract one volume from the other. You find the area under this triangle and the area under the other triangle, which is this one. If you put it up here, it's gonna be up here. And then whatever is not included in both, like you're gonna do this area here that is not included in this area. You subtract those two volumes, and that's how you solve for the storage volume, uh, the difference in the storage volume. So, and this is it for this video. I hope this is helping you to understand this table is very useful to understand how each method or study area is going to plot their own synthetic hydrograph. Um, Remember that all the reason we're doing this is because usually we are not given flow values as easily as we have been given so far. Sometimes we need to develop our own hydrographs, and these are called synthetic hydrographs. So this is it for this video. Good luck solving this problem. See you in the next video. Bye bye.